I will begin again on page 8. Given a dredging machine shoots 5,000 gallons per minute of a mud-water mixture to a stationary barge. The discharge nozzle of the machine has an exit area of 1 square foot and the mixture has a specific gravity of 3. What is the force on the barge that attempts to separate the machine from the barge? You know, in the figure, what's shown is a boat, essentially, that is spraying the mixture into a barge. So this is just pulling stuff essentially off the bottom of the river or pond or whatever this happens to be and spraying the mixture into the boat. Now, if you think about it, the stuff coming out here, this mud water mixture, is going to have some momentum, and that momentum is going to tend to push this boat because the boat has to push on the fluid that's coming out in this direction to decelerate it, at least with respect to the barge. So the question is, what's the force on the barge that attempts to separate the machine from the barge? Now, what kind of analysis should we use here? Well, we could use force equals mass times acceleration. That may not be the easiest because we don't know the acceleration, right? We don't know how quickly this stuff slows down. That may be difficult. How about energy conservation? Well, basically, energy conservation would just tell us that all of the kinetic energy here gets lost. And now it's not destroyed, but it's just converted into a different form. In fact, it would be converted into thermal energy. So that doesn't really help us. So momentum is the only way to go. And it's a kind of a dead giveaway. Since we're dealing with a fluid that's flowing, we need to use the equation that looks like this. Now this is in reality a vector equation for fluids, and it talks about basically just conservation of momentum. Now if the fluid leaves, let's see, it begins with momentum at A and has a different momentum once it falls into this boat, has a different momentum B, then there must have been some force applied to it to change its momentum. Now the velocity at B, once the fluid goes into the barge, its velocity is 0, so that's its final velocity. So what forces act on it? Well, the only force that acts on the fluid is force from the barge, so there's just one force to consider here. And I'm only really interested in the horizontal component of the force because as the fluid falls, it's going to obtain speed in the vertical direction because of gravity, but the buoyancy of the water is going to support the barge and the extra weight, essentially, of the flowing stream. But it will also provide force to decelerate the mass, the flowing stream, in the vertical direction. So the only piece I really have to worry about is the horizontal component, because that's the push, if you will, that will tend to separate the machine from the barge. So this force is the only piece that I'm interested in. Let me change that and call that P. So there's force P. Let me try a different color too to make sure this shows up on the video. So basically that's the only force acting. I need the mass flow rate, but mass flow rate, well, what is the mass flow rate? Well, it's the mass flow rate of this stuff coming out. Well, we could write that as the density of the flowing stream times the volumetric flow rate, the amount of volume per time that's going into the barge. Now, then the last thing we're left with is VA. Notice that I've gone ahead and I've just taken the X component in these equations. And let's see, what are we left with? Well, we need to expand this a little bit farther. The volumetric flow rate could be written as the velocity times cross-sectional area. Now, what velocity are we talking about? Well, we're talking about the velocity at the entrance. Well, the entrance really is here, or the initial. So this is, again, VA. So we have VA appearing twice in the equation, so we get negative rho VA squared multiplied by the cross-sectional area A. Now, we were not given the density, we were given the specific gravity of the flowing stream of that mud-water mixture. So this would be minus the density of water times the specific gravity of the mixture. I'll just put an M there for mixture, times the velocity at A squared multiplied by the cross-sectional area. What cross-sectional area? Well, the cross-sectional area at A. So let's make that clear. All right, so we're just supposed to figure out the force that tends to separate these two. Now, you have to be careful. I drew this force P in the negative direction, so I should have plugged in negative P here all along. Now be careful, the P is different than the rho. The rho is the density, the P is the force. I could have made it an R, it doesn't matter. But that's the force we're trying to find. So you notice that the negative signs cancel. And then basically that P is equal to the density of water. This is something you should have memorized. Now we're in English units, so it's 62.4 pound mass per cubic feet. The specific gravity was 3, so that takes care of the first two terms. The velocity at A, let's see, well I just realized, I've got 5,000 gallons per minute, so I really didn't even need, let's see, that's the volume flow rate. Yeah, so I really didn't need the cross-sectional area in order to solve this problem. But I do need the cross-sectional area in order to come up with the velocity. So let me, before I plug in numbers, let me instead write this equation in terms of the volumetric flow rate. So the volumetric flow rate V dot, some people use Q for this. You can use either one you want. I'll just write capital Q here as well. The volumetric flow rate is equal to the velocity of flow multiplied by the cross-sectional area. So if we rearrange for the velocity at A, we get the volumetric flow rate divided by the area. Now the reason that Q is used for the volume flow rate is because we typically use V for velocity, so having a V over here can be confusing. But I use a script V for my velocities and a capital V for my volumes. So hopefully this is clear enough. Anyway, so the force P now would be equal to the density of water times the specific gravity of the mixture multiplied by VA squared. But VA squared is going to be V dot over cross-sectional area A squared multiplied by area at A from here. So then this is the density of water, specific gravity of the mixture, volumetric flow rate V dot squared multiplied by, or actually that will cancel with one of these, so divided by the cross-sectional area at A. Okay, now we can plug in numbers. The density of the water is 62.4 pounds mass per cubic foot. The specific gravity is 3. The volume flow rate was given as 5,000 gallons per minute. Has to be squared, divided by the area at A, which was given as 1 square foot. Now, what you'll notice is that you've got pounds mass. You'll ultimately take these gallons and convert them to cubic feet. I didn't bring my book. I don't have conversion factors in front of me, and I don't remember how many cubic or how many gallons it takes to make a cubic foot. So I'll leave the conversions to you. Of course, we have minutes here as well, and you will want seconds. In fact, you should work on this until you get units of pounds mass foot per second squared, because that's what will come out at the end. Notice you have feet to the 5th power in the denominator. You're going to convert gallons into cubic feet. Once you square that, that will be gallons squared. But if you, I'm sorry, let me back up. You convert gallons to cubic feet. Once you square it, you'll have feet to the 6th power, which when divided by feet to the 5th power will just give you feet. And then when you convert minutes to seconds and then square it, you'll have square seconds. So this will work out. My point is, you're going to need a conversion factor to get to pounds force. So what you should do is then divide this by, well, let's see, 1 pound mass, 32.2 feet per second squared per pound force. The pound mass obviously cancel. Once you take care of the time units mismatch, that'll work out. And once you fix the gallons to cubic feet, all of this will work out and it'll be done. Like I said, I don't have my conversion factor with me, so I'll just stop this problem at this point and let you finish it. Okay, going to the next page, page 9. Given 2 plates move on frictionless guides, both have a mass of 4 kilograms. The restitution coefficient between the plates is 80% or 0.8. Let's see, plate is at rest. I think I meant plate B is at rest. But plate A has a velocity of 4 meters per second before impact. So we're supposed to find both plates' speed after collision and the spring's maximum deflection. The figure that we're given looks like this. The plates are drawn in cross-section so that you can see how they slide on the guide rails. So this is all one plate, it's plate B. Plate A, on the other hand, is the plate that's on the right and moving to the left at a rate of 4 meters per second. The thickness of these plates is 0.1 meters. Both of them are the same. We'd be consistent and label them below, dimension them above. And let's see, over here, plate B is supported by a spring that goes back to ground. The spring constant K is 500 newtons per meter. And the initial position of the plate is a ½ meter. The other thing that we're given is that the restitution coefficient E is 80%. Okay, as well, the mass of A is the mass of B is 4 kilograms. So we have 8 kilograms total in this system. Okay, we're supposed to find both plates' speed after collision. So let's figure out what we should do here. Force equals mass times acceleration won't help us very much. It'll be difficult to solve it that way, and besides, we can't use the coefficient of restitution very well in that method. Energy analysis will probably come into play when we figure out how fast this plate is moving after impact, because then we can figure out how far the spring is depressed. But momentum conservation is definitely the way we want to go, because it's a giveaway because we've got the coefficient of restitution. So let's set up the momentum equation. Now I'm going to take A and B as a system so that I can write the momentum of, the mass of A times the velocity of A initial, which is the momentum of A in the initial case, plus the mass of B times the velocity of B initially equals the mass of A times the velocity of A final plus the mass of B times the velocity of B final. Now notice B begins with no momentum, so that goes to 0. Now in this equation we've got one equation, two unknowns, and the two unknowns are the final velocities of the two plates. That's where the coefficient of restitution comes in. It just says that, well, the relationship between the initial and final velocities, or the relative initial and final velocities, is 80%. So it looks like this. The final velocity of A less the final velocity of B divided by the final, let's do it this way, the negative of the initial velocity of A less the initial velocity of B. Notice these two initial velocities are going to be more different than the finals, because there will be a higher relative velocity before impact versus after. So again, we have another equation with only two unknowns, same two unknowns as before. So let's solve this out. The easiest way is to probably just, well, I think in a previous problem I rearranged the coefficient of restitution equation. So this time I'll just rearrange the momentum equation. Say mass of A, velocity of A initial. Let's go with, we need both, so we'll just subtract one of these off. Mass of A, velocity of A final equals velocity of B final if we divide both sides by the mass of B. So there we have it. So let's plug that in here. Okay, so this would be VA final. Tell you what, let's make our lives easier. Let's go ahead and move this to the other side. So negative VA initial minus VB initial multiplied by E, okay, equals VA final minus VB final. But VB final is this whole mess. Okay? So minus this whole term. So that would be mass of A, VA initial, minus mass of B, VA final, divided by the mass of B. I may be sorry I went this way. We'll see. Okay, so now let's take the combined equation, which is here, and write the unknown is VA final. So we want to get it by itself. So let me just, I guess I'll just go ahead and copy the left-hand side of the equation again. And I'll separate out these two terms. So we'll have negative mass A over mass B, VA initial, but negative times negative is positive, so plus. You'll notice the mass of B will cancel, and all we will be left with is VA final. So actually that works out nicely. All right, so let's move this term to the other side and write that negative VA initial minus VB initial plus the mass of A over the mass of B, VA initial, just moving this term to the other side, and maybe not forget the E in there, equals, we've got a VA final here and a VA final here, so we have two VA final. And so VA final should be all of this divided by 2. Now I'm just going to go ahead and plug in the numbers. There's no point in playing with it any farther. VA initial, and I guess I should have noted that VB initial was 0 a long time ago, because then I could have eliminated some of this. Copying. There we go. So it'd have minus VA, well, I said I was going to plug in numbers. So minus VA initial times E, well that's 4. Now we have to be careful at this point. We have to set up a coordinate system so that we know whether this velocity is positive or negative. Usually we would take a coordinate something like this. So that means that VA initial is a negative thing. Right? Now this negative sign just comes from the equation. When I plug in VA initial though, I'm going to plug in negative 4 meters per second. And for the sake of space and writing, I'm not going to write the units. This is all consistent. We can tell the mass units will cancel, and the velocity will come out in meters per second. So anyway, negative of negative 4 meters per second times E, which is 0.8, plus the mass of A over the mass of B, well, both are the same, so that's just a 1, times VA initial. Well, VA initial, let's see, it's a negative 4, right? So negative 4. Don't forget we need to divide the 2 out, and we'll have units of meters per second. So let's see what we get for a VA final. All right, negative negative is positive, so we're going to have 4 times 0.8 less 4 times 1 is negative 0.8 over 2. So it looks like the final speed of A is negative 0.4 meters per second. So it's interesting that A continues to move to the left after impact. So here's VA final is 0.4 meters per second. Since I've already got the arrow to the left, it's understood that's a negative thing. Now you might ask, well, what about the spring during the impact? Won't it make a difference? Because doesn't it apply force? Well, technically, yeah, there would be some period of time that these two are in contact and moving together, but it's such a short period of time, and the spring does not begin compressed anyway. It's such a short period of time, and the force from the spring will be so low that we'll simply neglect that part of it. So we'll just assume the impact happens, and then the plate B immediately begins moving. So let's go ahead and solve for the final velocity of plate B. And let's just make sure that everything works out. Let's do a sanity check here and see if we're on the right track. I'm going to get rid of some of the intermediate stuff and plug in, first of all, let's see, I guess what I'll do is I'll plug in the velocity of A final and solve for the velocity of B final. But I'm not going to do it at the board. There's really no need. I'll let you go through that exercise. I'm going to note that the mass of A and B are the same, so I can just get rid of these. That'll make our lives a little easier. And then all I'm going to do is take the velocity of A initial, which is a -4, and I'm going to subtract off from it the final velocity. Now notice the final velocity is a negative, so if I subtract a negative, I will add a positive, so plus 0.4. Looks like the final velocity of B from this equation is -3.6 meters per second. Now let's find out if that works, right? Let's plug it into this equation and see what we get. So velocity of A final is -0.4 meters per second. Velocity of B final is -3.6. Notice the sign comes from the fact that we need the relative velocity. And the initial velocity of A is a -4 meters per second. Okay, so let's see what happens. So 3.6 less 0.4 from the numerator is 3.2 divided by 4, I get 0.8. And that checks because that's the correct value for the coefficient of restitution. So now we know how fast plate B is moving immediately after impact. And that's really all we needed. I went through and solved for the velocity of A because it was requested, but for part B, all we really need is the velocity of B. Now another thing you could ask is, after impact, how much energy was lost by comparison to before? So you could take 1/2 mv squared and calculate the initial and final kinetic energy and see how much energy was lost. There will be less energy after impact than there was before because it's not a perfectly elastic impact. In other words, the coefficient of restitution is less than 1. Okay, so now let's calculate the spring deflection. This is a pretty easy part because basically all of the kinetic energy in plate B will go into the spring. So the equation to write down is like this from chapter 13, which is conservation of energy. And what we're talking about here is when the two plates separate after impact and plate B is moving to the left. Well, then it has some kinetic energy, but when the spring is fully compressed, it will not have any kinetic energy. Expanding this term, we'll have 1/2 mass of B times velocity. What velocity? Well, the velocity after impact, and we called that before VB final. Okay. Now let's take care of the next term. What forces do work on the plate to get it to change its speed? Well, only the spring. So all we need is a spring equation. That would look like this: 1/2 K delta X squared less delta X squared. Now I always have to think about this to make sure I get it right. I know that this is going to be a positive thing. This needs to come out negative. So I know that this should be the initial deflection 1, and that should be the final deflection 2. The initial deflection is, of course, 0 because the spring is not compressed at all at the beginning. And we know that these need to sum to 0 because at the end there's no kinetic energy. So the question is really, how much is the deflection? So there's the unknown. We can cross off the halves, we don't need them. If we move everything around, we'll have mass of B, VB final squared equals K delta X2 squared. Okay, just the negative sign here comes out when I'm moving to the other side. Okay, so then delta X would be equal to the square root of the mass of B over K multiplied by VB final squared. And you could also take that velocity outside of the square root if you wanted to and say this is VB final root mass of B over K. All right, so plugging in the numbers, the final velocity. Now you have to be careful here because if I plug in a negative velocity, I'll get a negative delta X, and in a sense that makes some sense, but we're just talking about the deflection of the spring. So really notice in the energy equation that the velocity was squared. There's two possible roots of that. There's a positive and a negative root. So we just really need magnitudes here. So 3.6 multiplied by the square root of quantity mass, which was 4 kilograms, divided by K, which is 500 newtons per meter. We get a number, and that number is 0.322 or so. Well, what are the units? We have to think about units as well. So let's see. if we look at the units of the velocity, it's meters per second. And then we need square root of the mass, which is kilograms per, and then the spring constant, newtons per meter. Let me just put the meter up here. Okay, so there's the spring constant units. Now, a newton is a kilogram meter per second squared. So you see how the kilograms and the meters all go away. And basically, this term has units of seconds. So the seconds will cancel and we simply have units of meters. So we've proven that the spring deflects by about 0.322 meters. And that's the end of that problem. Okay, let's try the next one on page 10. Given a cylindrical tank rolls backward on a flatbed truck without slipping. The center of the tank has a velocity of 10 feet per second to the left relative to ground. The truck has a forward speed of 30 feet per second. Let me sketch this so that you can see what I'm looking at. So here's the truck. It's a flatbed truck, so it has wheels in the back as part of the frame. The truck's forward speed is 30 feet per second. There's the ground, by the way. And there's the cylindrical tank on the back. Now there is contact between these two, and the tank rolls without slipping. The center of the tank has a velocity of 10 feet per second relative to the ground. Now we're supposed to, oh, and by the way, the radius of this thing is 2 feet. The radius of the tank is 2 feet. And then there's a point of interest here called B. All right, we're supposed to find the angular velocity of the tank. Now, if you stop and think about it, you'll realize that this point on the body on the tank is moving forward at 30 feet per second because there's no slippage there. But this point is moving backward at 10 feet per second. So if we want to analyze that body's motion, yes, the body is a round body like this, and this point has a speed of 30 feet per second. I'm not going to use the units for a moment. This point has a speed of 10 feet per second. These are both relative to ground. But if we need the angular speed, we'd like to know where the tank is rotating, or where its center of rotation is. Its center of rotation is not at its center, right? At least not relative to the ground. And we need the angular speed relative to ground. So let's see what we can do. Well, if this point on this body is moving that way at 30 feet per second, and this one's moving this way at 10 feet per second, there must be a point somewhere on the line between the two that has no velocity. So we have to consider this as a larger body. We're not as concerned anymore about the particular shape of the body, okay? Now, where would it be? Well, if this point's moving, you know, if I just drew a line here and said, this point's moving at 30 feet per second, and this point is moving at 10 feet per second, then you would probably realize, well, the center of rotation's here somewhere. Because with a longer moment arm, or longer distance, the profile will look something like this. Let me make these a little closer to scale. So there's, say that's a 10 unit, and then this one needs to be 3 times that length. So something about like that. Then you would realize that there would be a linear velocity profile between those two. And it makes sense that there's a zero velocity here because as you move closer and closer to the actual center of rotation, what you'll find is that you've got a point that's closer to this slower speed point. Okay? So where is that point? Well, it just scales proportionally, right? Basically, the angular speed of the body is the same whether I'm looking at this point or this point. And the angular speed would be equal to, let's call this L1, let's call this L2. Okay. The angular speed would be L1 times 10, right? No, let me get this right. What I'm doing is using V equals omega R. So the scaling should have been different. I'm not thinking right. The length R is like L1. Okay, so omega would be V1 over L1, right? Just rearranging the equation. And it would be the same thing as V2 over L2. Basically, what we'd have is something like this. L1 over L2 equals V1 over V2. So the ratio of those two lengths is equal to the velocity ratio. So that's a third. Okay. So there's the length ratio. Well, what's this total length? This is one equation and two unknowns, right? L1 and L2 are both unknowns. Well, that total length that I was looking at is just the radius. So basically what we have is L1 plus L2 is 2 feet. And you can figure out, you know, it's pretty obvious then that we've broken this up into 4 parts, right? Because L1 is one of those parts, L2 is 3 of the parts. And so it's pretty obvious. You can solve the equation if you want. But L1 is a half foot, whereas L2 is 1.5 feet. Of course, if you take that ratio, that's 1 to 3. Okay, so there's the lengths. And so basically the center of rotation on this thing is down by a half foot, or basically 6 inches. Okay. Make that an arrow where you can see that it's an arrow. So there's the center of rotation. Now that we know where the center of rotation is, we can take either of these ratios and find the angular velocity. So 10 feet per second divided by a length of 1/2 foot, or basically this bit here, would give us a rotation speed of 20 radians per second. So there's the rotation speed. So the answer to part A is that the angular speed is 20 radians per second. Now for part B. We're supposed to find the magnitude and direction of the velocity of point B. Now a lot of students will look at point B and say, well, it's right here, so it must be moving straight up. But that doesn't make sense. The center of rotation is not right here, it's down a bit. And so what you have to do is drop a line to the point from the center of rotation and then draw the velocity perpendicular to that line. So basically what we need, if we want to find the magnitude of that velocity, we need the angular speed, check, we have that. But we now need this radial distance. Okay, and that distance, if I extract a triangle over here, it's going to look like this. It'll be 2 feet, because that's the radius on this side. It's a half foot, because that's the height on this side down to the actual center of rotation. So what we need is the length of this side. We need 2 squared plus a half squared, and the square root. It's Pythagorean's theorem. So that would be 4 plus a half squared, and then the square root of answer. Looks like it's 2.06 some odd. So 2.0615, so on and so forth. Okay, so there's the radial distance. Now, if I'm going to calculate the velocity of point B, and I have the radial distance now to point B, I can simply take 20 radians per second multiplied by that 2.0615 feet. My diagram's getting messy, so let me get rid of some of this. Okay, so basically just multiply 20 by what I have in my calculator for my last answer, and it looks like that the velocity of point B is 41.23 or so feet per second. Okay. Now if we want the direction, what we have to do is realize that it's coming off perpendicular here, and I'll leave it to you to figure out the vector components if you want to do that. But the basic thrust of the question was, is point B moving straight up or not? And obviously it's not. Point B is actually moving up and to the left. All right, that's as far as I wish to go with that one. Let's go to the next problem on page 11. I'll read it and I'll sketch it, because you really need a figure. If you're not looking at the packet, you should download it. It's just a PDF file. And go to the page so you can see this. Collar B is moving to the right at a constant speed of 10 meters per second. Determine the linear velocity of point A and the angular velocity of the collar attached to point A. There's actually 2 collars here. Really, I should have said that there's a slider at B, but I didn't. Okay, so there's an arced member that has a collar sliding on it. That collar is collar A. There is, let's see, I'll try to get this as accurate as I can. Connection to slider B. And I'll just draw the skeleton diagram. You can see the mechanism in the PDF file. We're given some dimensions here. First of all, the center of this circle is also on line with the slider, and it's 2 meters. The distance between A and B at this particular position is 1.5 meters. Now, we know that B is moving to the right at 10 meters per second, and we're supposed to determine the linear velocity of point A and the angular velocity of the collar attached there. Okay? So, this is an instant center problem, so the first thing we'll want to do is locate all the instant centers. How many are there? Well, we've got body 1 here. It's called A, body 2. Body 3 is the connecting link, and body 4 is the slider B. So we're going to have 6 instant centers. So let's put let's lay down a diagram for the bodies and figure out what instant centers we have. Well, let's put instant centers in green so that hopefully they don't stand out. So the instant center between 1 and 4 is at the pin. In other words, this pin has the same speed on, and I'm sorry, 1 and 4. Actually, it's 3 and 4. This pin has the same speed on body 3 as it has on body 4. On the other hand, the instant center between 2 and 3 is here at the pin to body A. All right, well, that's 2 of them. That's 2, 3, and 3, 4. How about the instant center between, let's see, what else is obvious? How about between 4 and 1? Well, remember, since this is pure sliding motion, then the instant center between 4 and 1 is at infinity along this line. So 1 to 4 has been found. A lot of students look at this and say, well, you say it's at infinity, we can never get there, so we haven't found it. Well, we do know where it's at. And remember, the instant centers are just for characterizing the motion. It doesn't matter where they end up, as long as we can use them. And we know they're not real things. That doesn't matter. They allow us to analyze. Okay, how about the instant center between body 1 and body 2? Well, body 2 is here. Body 1 is ground. Where is a point on body 2 that has the same speed as body 1? This is one that really confuses students. Imagine extending body 2. As it moves, what point would remain stationary? In other words, what point would have the same velocity as body 1? It would be this point. So that is the instant center between body 1 and body 2. Now we have enough instant centers to find all the rest. If we want to find 1, 3, for instance, we will connect 1, 2 with 2, 3. Let's see, 1, 2 is here, 2, 3 is here, so that's this line. 1, 2 with 2, 3, and connect 3, 4 with 1, 4. Where is 3, 4? 3, 4 is right here. If we connect it to 1, 4, then we have this line, right? We just have this vertical line here. Now you'll notice that the connection of 1, 2 with 2, 3 is a vertical line. The connection between 1, 4, 3, 4 is a vertical line as well. No, wait a second, did I do that right? Yeah, 1, 4, 3, 4. Okay? So we have 2 parallel lines. Well, parallel lines intersect at infinity. So where is the instant center between what we're doing? 1, 4, 3, 4. Where's the instant center between body 1 and body 3? Well, it's at infinity. Well, that doesn't really seem very satisfying, right? How is that possible? Well, let's stop and think about this. At this moment in time, body 3 is right here. What's this link doing? It's moving back and forth. What's this link doing? Well, it's at the top of the curve, and so it literally is moving back and forth as well. Both of these are moving back and forth, right? That's their motion. There's no rotation at all, because neither one of these have any motion in this direction. And so, basically, link 3 is not rotating. that means that its instant center is at infinity, just like this one is. So we have indeed found the instant center between these two. Okay? Now how about the instant center between body 2 and body 4? Well, here's body 2, here's body 4. Okay? Where do they have the same instant center? Where is their velocity equal? Let's find out. We will connect 1, 2 with 1, 4. Okay, so where's 1, 2? It's right here. Connected to 1, 4, that's this line. You know something about it. 1, 2 with 1, 4. Connect 2, 3 with 3, 4. 2, 3 is here. 3, 4 is here. So the instant center between body 2 and body 4 is here. We verify that I did that properly. 1, 2 is here. 1, 4 is at infinity. That makes sense. 2, 3, 3, 4. Let's see. 3, 4 is here. 2, 3. Yeah. So there's the instant center between body 2 and body 4. Now, if you think about it, that's really just one instant center. Actually, everything is an instant center between body 2 and body 4, because in this particular point in time, every point on these two bodies is moving the same. No, wait a second. Let me think about that. No, that's not really true. That's not true. Because at this point, body 2, while it's translating, it's also going to be rotating. So if I were to extend body 2 out, because of the rotation, in addition to the translation, it would have a different speed. So I was wrong. I24 is the only point where body 2 and body 4 have the same speed. Now notice we were asked to find the velocity of point A. Well, point A is right here. It has the same velocity as point B, so it's 10 meters per second. So the velocity of A is 10 meters per second to the right, just like the velocity of block B. Next, we're supposed to find the angular velocity of the collar attached to point A. So we need the angular velocity of this collar. How fast is it rotating? Well, it's rotating about this point, and V equals omega cross R would tell us that its angular speed of body 2 would be the velocity of point A divided by the distance between I12 to I23. Okay? Or better yet, to A. Because that's the point on the body where we know its speed. So this is just 10 meters per second divided by the distance of 2 meters. And that's just 5 radians per second. Now is that clockwise or counterclockwise? Well, since it's moving this way, then you realize there's a velocity profile that looks like this. And so it must be rotating clockwise. So that is a clockwise rotation. Okay? One more problem to go, and then I'll wish you luck on the exam. Page 12. The winch delivers a horizontal towing force, F, to its cable at A, which varies as shown in the graph. The mass of the bucket is 70 kilograms. The bucket is already moving upward at a speed of 3 meters per second when time equals 0. Determine the speed of the bucket when the time is 18 seconds. Okay. Now, there's a couple things given. First of all, I will draw the figure. There's a rope. The rope wraps around a couple of pulleys. One pulley's on ground, along with the motor that's doing the pulling. The bucket is connected to the rope by a pulley, and its velocity starts off upward. Now, if we take a point A, there's a force F being applied. Now, the force in the cable at F varies over time. In fact, another thing that was given was the force as it varies over time. And the force begins at 360 newtons and remains at 360 newtons for 12 seconds. The force then increases linearly to 600 newtons by the time 24 seconds have elapsed. Notice we're not interested in this. We're interested in what happens at 18 seconds. Okay? excuse me. Now, when you see force and time, you should realize this is probably a momentum type problem. And so we should write a momentum type of balance. So the only problem is the force being applied here is not actually the force being applied to the bucket, because the force being applied to the bucket is actually twice that force. Okay? So if we consider just the bucket's motion, we need the impulse of the forces over time. Now you might look at this and say, well, all I need to do then is say the mass of the bucket times the initial velocity plus the integral of, I'll just put 2 times the force over time, equals the mass times the velocity after the 18 seconds have elapsed, right? So no big deal. I'll just add up the area from 0 up to 18 seconds. And there's a little bit of geometry, but that's straightforward. That will be the impulse. I'll multiply it by 2 and be done with this. There's one problem. You've forgotten force. There is another force acting on this bucket over that time. Remember, there's still weight acting on it. And so really, when we write this equation and we just write F dt, what we really mean is sum of forces. What all forces act on the bucket during the time interval. All right, so let's see. Let me rearrange this a bit because we're just interested in the velocity after the time has elapsed. So we'll write V1 plus the integral over mass with respect to time is V2. Now the forces, we have to sum all of the forces. There are in fact 2F, basically, the area beneath this curve. We can figure out that part, but we have to subtract mg. That's the sum of the forces that acts on the bucket in order to change its velocity. Okay? Now it's pulling upward, so obviously the velocity is going to increase. It's going to move upward. You can say, well, what about the fact that the motion of the bucket is half the speed of what's going on over here? That doesn't matter. That doesn't make a bit of difference. We're not analyzing distance traveled, we're analyzing velocity. That's all we really care about. We don't care how far it goes during that time. So, let's see if we can do this. First of all, let's get the area beneath this curve, which really I've called F dt. Hopefully this is not too confusing. In fact, I'll tell you what, let's make it a little clearer by saying 2 times the integral of F over time over mass minus integral mg dt over m equals v2. Okay? So that way I separate out the forces and make it clear that this bit here is just this area that I've shaded. Okay, so this is the integral of force over time that comes from the graph. Okay? Now you'll notice that the mass in the second term goes away. G is a constant, so it just comes out. So basically we can write, I tell you what, let's go ahead and plug in numbers. V1, the initial velocity, is 3 meters per second upward. Now plus 2 times, let's figure out the area in this graph. This bit here is just a rectangle, so we need 360 times 12. When you do that, probably do it in my head, but I may make a mistake. So when you do that, you get 4,000. $320. Now, I probably should have just extended this over and made it a larger rectangle, so let me change my mind and do that. And then I'll add on that little triangle at the end. So instead of that, let's take 18 times 360. That'll be better. So 6480, and the units are Newton seconds. Now let's take care of the triangle. Now the triangle dimensions are what we need to figure out. The base of it is easy, right? It's just 18 less 12 is 6. So let me extract the triangle over here so you can see it. Let's see, this point's 12, this one's 18, so the difference between those two is 6. And now I need the height of the triangle. Well, we don't know the height of this triangle. We do know that there are, let's see, 12 seconds from here to here. And we know from here to here that there are, what, 240 newtons? So that breaks up nicely, right? The slope of this then is, let's do it this way, the slope is 240 per 12. So that is what, 20? Okay, so for each second you move along, you get another 20 newtons. So if we move along 6 seconds, then we should get an increase of 120 newtons. Let's do a sanity check and see if that makes sense. This bit here is half of the distance, right? It's 6 seconds. In 6 more seconds, we should get the total, in fact we do. 120 plus 120 is 240. 240 plus 360 is 600, so that makes sense. So now to get the area of this triangle, all we're going to do is take 6 times 120 over 2. And that's 360 Newton seconds. Okay, so now that integral that I circled up here, this area is just 6480 plus 360. So 6480 plus 360. So I've got 6840 Newton seconds. Now the mass is the mass of the bucket. We were told that the bucket is a 70 kilogram bucket. Now before we move on, let's work with the units. I'm going to leave the seconds here and expand the newtons into kilogram meter per second squared. You'll notice that one of the seconds go away, the kilograms go away, and we have meters per second. So the units are consistent. We have meters per second for the velocity, meters per second for this ratio, and then finally this would just be g times delta t. Let me show you that up here. The g would come out because it's a constant. So we have the integral of dt from state 1 to state 2, which is just a, an 18-second interval. So this would be minus g, which is 9.81 meters per second squared, multiplied by 18 seconds. Notice that we get meters seconds again. And that should be equal to the velocity at state 2. So let's plug in the numbers, see what we get. And that'll be it. So 6840 times 2 divided by 70 gives me this term. Plus 3 less this term. 9.81 times 18. So I get 21.85 or so meters per second. So it's really 21.84857 yada yada. Okay, so there's the speed of the bucket after that force has acted on the bucket for 18 seconds with that particular profile. Best of luck on the exam to you, and I hope you have a good summer break.